Hi, Chem students, and welcome to a lesson over electrons. Please have out your notes and something to write with.
Okay, orbital diagrams, these are kind of foreign to you. Show with an arrow notation how the electrons are arranged in atomic orbitals for a given element. So this should really correspond with that Aufbau order, except instead of writing out 1s2, we're doing it as arrows instead. Okay, so one orbital is represented by a line, just like I showed you earlier. So this is the first one, 1s. Okay, then the next line is 2s. Now what's weird is, remember how we talked about P? It has 3 orbitals. So I'm going to have to represent that with 3 lines. Okay, and then if I go to 2s, well, s is only 1 orbital. That's why I'm drawing 1 dash. And then again, P has 3 orbitals, so you need 3 dashes. This is always how you're going to represent these orbital diagrams. Okay, so I have examples of carbon and fluorine here for you. Well, how many electrons does carbon have? It has 6, so we need 6 arrows. So I fill up my 1s2, 2s2, and then 2p2. Right? So I have 2 arrows. Notice how I filled them singly? I'll go back and pair if I need to. Like in fluorine, it has more electrons. So I fill up my 1s2, because 2 arrows for 2 electrons, 2s2. Then we're in 2p, so 2p1, 2p2, 2p3. Now I'm going to go back and pair 2p4, 2p5. And so if I count all my electrons, 2, 4, 6, 8, 9, that should be the total electrons in my atom. So try magnesium and argon on your own, please. Okay, noble gas configuration. This is the shorthand way of writing out that Aufbau order. The Aufbau order can be very cumbersome, so we came up with a cheat for it called the noble gas configuration. Let's look at some examples. Okay, the noble gas configuration. Say I ask you to write out strontium. Okay, extremely cumbersome. I didn't even want to write it out, so I put the key up here for you. This would be strontium. It's crazy, crazy long, okay? Because strontium is located right here. So if I have to start at the very beginning, it's going to take me forever to write out the electron configuration, okay? So I cheat and I do a noble gas configuration starting at the noble gas in front of strontium, which would be, in this case, xenon. So this group, group 18, these are your noble gases. You like noble gases because they give you a cheat on your configurations. So I'm going to start with xenon then, instead of at the top with hydrogen. And then all I have to do is write what's after xenon that gets me to strontium, which would be 5s and then 2 electrons, right? So this would be the noble gas configuration. Oh, I messed up. It's not xenon that you're starting with, it's krypton. Sorry, this periodic table is so small, I can barely read it. This says Kr, not Xe. So I stand corrected on this one. Make sure you can see your periodic table when you're doing this. Okay, the next one is manganese. Again, terrible to write out, okay? But, and it's right here, I can do a cheat. So I'm going to choose the noble gas in front of it. This time I can see that. It says argon. So argon, and then what's after argon? 4s2, 3d5. And then bismuth. Okay, bismuth is probably one of the worst ones. It's all the way down here. So I'm definitely going to use the cheat. This time, it's really xenon, okay? And then I have to do everything after xenon that gets me to bismuth. Something I want you to notice. Do you see how it says 4F14 here? Very important, okay? So after xenon, I come down here to 6s2. This lanthanide series is inserted right after 6s2. So that's 4f14, then I can come back and hit 5d. Okay, so that's a really important point to make.
So valence electrons, they're the electrons in the outer energy level of an atom. We say that they're like the front lines of an army because they are the ones involved in chemical reactions. Valence electrons are shared or transferred during these reactions. The number of valence electrons that an atom has is directly responsible for an atom's chemical behavior and reactivity.
I want to go ahead and remind you of what a segment of the electron configuration looks like and what it stands for. The number in front is the energy level, which correlates with the period on the periodic table. The letter is the sublevel, and then the exponent is the number of electrons within that sublevel. So, the number of valence electrons can be determined from the electron configurations. What we're going to do is we're going to count all the electrons in the outer or the highest energy level for that atom. So starting with lithium, we've got 1s2, 2s1. Okay, 1 is a very low energy level. It's the lowest one on the periodic table. 2 is higher. So how many electrons are in that energy level? There's only one electron. So it has one valence electron. One electron in that outer energy level. Beryllium, 2 is the outer energy level with 2 valence electrons within it. For beryllium, 2 is the outer energy level. Now it's in the S and the P sublevel, so we have to add those electrons together. That's 3 valence electrons in the outer energy level. So this pattern continues. With carbon, we've got 4. With nitrogen, we have 5, oxygen 6, fluorine 7, and neon has 8. So for the dot structure for these, what you do is you just write the symbol. So I'm going to write all my symbols first. Okay, so you have the symbol, and then you represent with dots the valence of electrons. So with lithium, there's 1 valence electron. Beryllium, there's 2. So I like to put the dots opposite of each other. With boron, there's 3. So I kind of just go clockwise. With carbon, there's 4. Okay, after you have 4, then of course comes 5. But you go around once, and then at 5, you make your first pair. So the rule is, at 4, you go around once. You should not have any pairs 1 through 4. But at 5, you'll see your first pair of electrons. Okay? At 6, we're going to have 2 pairs and then 2 that are single. For fluorine, we've got 3 pairs and then 1 all by itself to make 7. And for neon, you'll have 4 pairs, making a total of 8 valence electrons. That's just the pattern you should follow when drawing your electron dot structures. So the number of valence electrons for the representative element groups follows an easy pattern from 1 through 8, going across the periodic table from left to right. You see the pattern. It's easy. 1, 2, 3, 4, 5, 6, 7, 8. There is an exception to this, though, and that's helium. Helium only has 2 electrons. It's impossible that it would have 8. So helium, on some periodic tables, will actually be located above beryllium. Okay, notice that the elements in a group, also called a family, all have the same number of valence electrons. For example, group 1 elements, known as the alkali metals, all have 1 valence electron. Therefore, they will behave in very similar ways. So try this. Find an element on the periodic table that has the same chemical reactivity as sulfur. Here's sulfur. So this is very easy to answer. Any element in the same group will react the same. So oxygen is a very good answer for this. Here's a diagram of the electron dot structures for all the different atoms in those groups. So notice here that they all have the same number of dots, except helium is kind of the oddball. Like I said, it would fit nicely right above beryllium.